For decades, the most honest answer to the question, when will quantum computers beat supercomputers, was always the same. Not yet. Maybe in 10 years, maybe 20, maybe never for most practical problems. That was the cautious consensus from people who actually understood physics. And then, between December 2024 and October 2025, a series of events happened that forced the entire scientific community to update that answer. Not to, yes, quantum has won, because that would be too simple and the reality is more interesting and more complicated than a single headline can capture, but to something more unsettling. The boundary between what quantum computers can do and what classical supercomputers can match is no longer theoretical. It is being drawn in real time, in peer-reviewed papers, in published nature studies, in live demonstrations on hardware that exists today. And depending on which lab you look at, depending on which problem class you choose, the answer to whether quantum has permanently surpassed the supercomputer is somewhere between yes on specific things and yes, and classical computers can never close that gap. This is the story of how we got here, what it actually means, and why the question mark in the title is doing more work than you might think. To understand what any of these quantum advantage claims actually mean, you first need to understand what the argument between quantum and classical computing is really about. A classical computer, whether it is a gaming laptop or the world's most powerful supercomputer, operates on bits. Every piece of information is a 1 or a 0. It processes these bits sequentially or in parallel, but it always processes definite, concrete information. A quantum computer operates on qubits, which can exist in a superposition of 0 and 1 simultaneously. This is not a trick of language. It is a physical reality arising from the laws of quantum mechanics. When you have 100 qubits all in superposition, the quantum processor is simultaneously processing 2 to the power of 100 states, a number with roughly 30 digits. No classical computer can hold that many states in memory, let alone process them. For certain classes of problems, particularly those involving exponentially large state spaces, like simulating quantum systems, breaking encryption, or optimizing across enormous combinatorial landscapes, quantum computers have an advantage that is not just faster, but fundamentally different in kind. The question the field has been trying to answer for 30 years is, can we actually demonstrate that advantage on real hardware, doing something real and verifiable before classical algorithms find a way to catch up? The first major salvo in the 2024 to 2025 quantum advantage war was fired by Google in December 2024, when the company unveiled its Willow processor. Willow is a 105-qubit superconducting quantum chip manufactured at Google's facility in Santa Barbara, California. Google ran Willow through a benchmark called random circuit sampling, which is considered the classically hardest benchmark that can be performed on a quantum computer today. The result was the number that traveled around the world in hours. Willow completed the benchmark calculation in under 5 minutes. The world's fastest classical supercomputer at the time, Frontier, the 1.353 exaflop system at Oak Ridge National Laboratory in Tennessee, would require 10 septillion years to complete the same calculation. To write that number out, it is a 1 followed by 25 zeros. The age of the known universe is approximately 13.8 billion years. 10 septillion years is not just longer than the age of the universe, it is longer than the age of the universe, by a factor that makes the age of the universe look like a rounding error. Like and subscribe right now, because those are the kinds of numbers this story deals in, and we are just getting started. The Willow result was extraordinary in scale, but was immediately met with a familiar criticism from the scientific community. Random circuit sampling is a benchmark specifically designed to be hard for classical computers and easy for quantum ones. The computation itself produces essentially random output, a statistical distribution of bit strings that has no direct practical application. Critics, and there were credible ones, pointed out that the same quantum supremacy claim Google made in 2019 with its earlier Sycamore chip was later qualified when researchers demonstrated that classical algorithms could simulate the same benchmark using clever approximations. The worry was that Willow's 10 septillion year classical equivalence was a number derived from a computation that no one would ever actually want to run on a classical supercomputer, because no one needs the answer. The gap was real, but its relevance to real-world problems was disputed. Hartmut Neven and Vadim Smilyansky, the lead researchers at Google Quantum AI, were aware of this criticism, and in October 2025, they answered it. On October 22, 2025, Google announced the first ever verifiable quantum advantage on hardware. The algorithm they demonstrated was called quantum echoes, and it is fundamentally different from random circuit sampling in two ways that matter enormously. First, Quantum echoes is based on out-of-time order correlators, a physics measurement technique used to study chaotic quantum dynamics in systems ranging from molecules to magnets to the interior of black holes. It is a real physics experiment with real scientific value, not a contrived benchmark designed to make quantum hardware look good. Second, and this is what the word verifiable in the name means, the algorithm produces a deterministic, repeatable result that can be cross-checked against any other sufficiently advanced quantum computer. Unlike random circuit sampling, where the output is a random bit string that is nearly impossible to independently confirm, quantum echoes produces a stable quantum observable, a specific numerical value, that can be reproduced and verified across different quantum systems. This is critical because verifiability is what makes a quantum computation scientifically useful. If you cannot confirm the output, you cannot trust it for real applications. Google ran quantum echoes on 65 of Willow's 105 qubits and measured the out-of-time order correlator for a chaotic quantum system. The result? Willow completed the algorithm approximately 13,000 times faster than the best classical algorithm running on Frontier, one of the world's fastest supercomputers. For certain individual data points in the quantum echoes experiment, simulating the equivalent result classically on Frontier would take an estimated 3 or more years per data point, whereas Willow generated the same data points in seconds. The researchers also demonstrated a proof-of-principle experiment using quantums. Echoes as a molecular ruler, a technique to measure distances between atoms in molecules using nuclear magnetic resonance data, suggesting that the algorithm has direct applications in chemistry and materials science. Google's team explicitly framed this as the first time in history that a quantum computer successfully ran a verifiable algorithm that surpassed the ability of even the world's fastest supercomputers. Not on a synthetic benchmark, on a real, reproducible, scientifically meaningful computation. Before Google made that October announcement, however, a different company had already staked its own claim to quantum supremacy and ignited a controversy that exposed just how hard the question of permanent quantum advantage really is to answer. In March 2025, D-Wave published a peer-reviewed paper in the journal Science titled Beyond Classical Computation in Quantum Simulation. D-Wave is a company with a fundamentally different approach to quantum computing than Google, Quantinuum, or IBM. While most quantum computing companies build what are called gate-based quantum computers, where you manipulate qubits with sequences of quantum logic gates, D-Wave builds quantum annealing systems, which are specialized machines designed to find low-energy states of complex problems. It is a narrower computational paradigm, but it is commercially available today and has been for years. In the science paper, D-Wave's researchers used their Advantage 2 quantum annealing processor, which features roughly 1,200 superconducting qubits, to simulate the quantum dynamics of magnetic materials, specifically the non-equilibrium behavior of magnetic spin systems across a range of lattice geometries. The simulation involves studying phase transitions in complex magnetic structures with different shapes and sizes, cubic lattices, diamond lattices, Bicklick lattices, across a range of conditions from easy to computationally intractable. D-Wave's CEO, Alan Baratz, described the core result in blunt terms. Their quantum computer solved a complex magnetic material simulation problem in approximately 20 minutes. D-Wave's calculations showed that performing the most complex version of the same simulation on the Frontier supercomputer using the best available classical algorithm, matrix product states, would require nearly 1 million years, and it would require more than the world's annual total energy consumption to power the classical computation. D-Wave called this the world's first and only demonstration of quantum computational supremacy on a useful, real-world problem. But the ink on that science paper was barely dry before the challenges arrived. Before D-Wave's press conference had even finished, 2 separate classical simulation papers appeared. A team at the Flatiron Institute in New York, led by Joseph Tyndall, developed a new classical approach based on belief, propagation, tensor network simulation, BPTNS, an artificial intelligence-assisted algorithm adapted from a 40-year-old mathematical technique. Their method reportedly reproduced certain results from D-Wave's experiments on classical hardware in a fraction of the time D-Wave claimed would take 1 million years. A separate team at the École Polytechnique Fédérale de Lausanne in Switzerland, led by Linda Moron and Giuseppe Carleo, used time-dependent variational Monte Carlo techniques to simulate quantum annealing in spin glass models on classical machines, finding that classical simulations could rival the quantum annealer on systems up to 128 spins in a 3-dimensional diamond lattice. One popular report claimed that a researcher at NYU was able to reproduce similar calculations on a regular laptop in 2 hours using tensor networks. Like and subscribe. Because what happened next in the scientific back and forth is exactly the kind of collision of evidence and counter-evidence that shows you why the word permanently in this video's title is carrying an enormous amount of weight. D-Wave pushed back hard and with specific technical arguments. CEO Alan Barrett's issued a detailed response stating that the Flatiron Institute's BP-TNS algorithm, while a genuine and meaningful contribution to the classical simulation state-of-the-art, did not reproduce the full scope of D-Wave's science result. Specifically, D-Wave argued that the classical teams did not attempt the most complex lattice geometries D-Wave used, did not reproduce the largest simulations in three-dimensional lattices, did not simulate the low-precision ensembles where quantum correlations grow fastest, and did not produce the full state and fourth-order observables reported in the original paper. D-Wave also published a follow-up paper on ARCF, demonstrating directly that BP-TNS fails for strongly coupled three-dimensional spin. Glasses on cubic and diamond lattices. The company maintained that the cases classical teams successfully simulated were a subset, a relatively easier subset, of the full range of problems covered in the science paper, and that the hardest instances remained beyond the reach of classical methods. As of mid-2026, this scientific debate is still ongoing, with both sides publishing additional results. What it demonstrates is something important and nuanced. The boundary between quantum and classical is not a clean line. It is a moving frontier, and it shifts every time researchers on either side develop new algorithms or techniques. The D-Wave controversy exposes the core tension inside every claim of permanent quantum advantage. Classical computing is not static. Every time a quantum computer demonstrates advantage on a specific problem, teams of mathematicians and computer scientists begin working on new classical algorithms to close the gap. This happened to Google in 2019. Their Sycamore quantum supremacy claim was qualified when classical improvements narrowed the gap. It happened to D-Wave in March 2025 on certain parts of their result. It is part of why Google's October 2025 Quantum Echoes result is significant in a different way. The algorithm models a physical experiment, which means the output has to satisfy precise physical constraints, not just statistical ones. You cannot approximate a verifiable out-of-time order correlator the way you can approximate a random bit string distribution. The verification requirement creates a qualitatively harder target for classical algorithms to match. That is the nature of the quantum advantage that makes it more durable. Beyond the Google and D-Wave results, 2025 also saw IBM enter the quantum advantage conversation with more measured but commercially significant claims. In June 2025, IBM partnered with Riken in Japan, using the IBM Quantum Heron processor alongside Japan's Fugaku supercomputer, to simulate molecules at a level that neither system could reach independently. IBM researchers published a paper in July 2025 explicitly stating that quantum computing had arrived at a place where it functions as a useful scientific tool capable of performing computations that the best exact classical algorithms cannot. That is a carefully worded claim, but an important one. IBM was not saying quantum has won universally. They were saying that for specific problem classes, particularly quantum chemistry simulation of molecular interactions at the quantum mechanical level, hybrid quantum classical computing is already beyond what the best purely classical methods can achieve, even when those classical methods include the most powerful supercomputers on Earth. And IBM added that they expected industry consensus on real quantum advantage across a broader range of useful problems to be achieved before the end of 2026. The deeper question, the one the question mark in this video's title is really asking, is whether any of these demonstrations represent a permanent crossing of the line, or whether classical computing can always eventually catch up on any given problem. The honest answer, based on everything the physics tells us, is that on certain problem classes, quantum advantage is not just faster, but mathematically permanent. The most famous example is Shor's algorithm, which factors large integers exponentially faster than any known classical algorithm. It is not that classical computers are slow at factoring. It is that the scaling of classical computation with problem size is fundamentally different from quantum. As the numbers get bigger, classical factoring time grows exponentially. Quantum factoring time grows polynomially. That gap is not closable by better classical algorithms. It is built into the mathematics of the problem. The same structural argument applies to certain classes of quantum simulation problems. Simulating quantum mechanical systems using quantum computers is natural because the quantum computer operates by the same physical laws as the system being simulated. A classical computer is always operating a model of quantum physics. A quantum computer is operating the physics itself. What keeps the question mark alive in practice today, in 2025 and 2026, is that we are still in the early era of quantum hardware. The current generation of quantum processors, Willow, Helios, the D-Wave Advantage, IBM's Heron series, are powerful enough to demonstrate quantum advantage on specific, carefully chosen problems, but not yet powerful enough to run the fault-tolerant algorithms that exploit the permanent mathematical advantages of quantum computation at scale. Shor's algorithm needs thousands of fully error-corrected logical qubits to factor RSA-level cryptographic keys. Today's best systems have tens of logical qubits. The gap between demonstration and deployment is real, and it is being closed faster than most people expected, but it has not been fully closed yet. What has changed in this period, what is genuinely new and genuinely historic, is the nature of the demonstrations. Before December 2024, every quantum advantage claim could be credibly challenged. Either the problem was artificial, or the results were not verifiable, or a clever classical algorithm eventually closed the gap. After Google's quantum echoes result in October 2025, for the first time in history, a quantum computer ran a verifiable algorithm with a real physical interpretation and produced results 13,000 times faster than the best classical approach on the world's fastest supercomputers, in a way that can be independently reproduced on other sufficiently advanced quantum hardware. That is a qualitatively different kind of milestone, and it came on the heels of D-Wave's science paper, contested as parts of it are, which showed that on a specific class of magnetic materials, simulation problems, quantum annealing systems, are performing computations that would take classical supercomputers millions of years and the entire world's annual energy supply to replicate. Even accounting for the classical team's partial rebuttal, the hardest instances in D-Wave's result remain beyond what classical algorithms can efficiently match. The implications of this moment extend across almost every field that depends on computation. Drug discovery is perhaps the most immediately impactful area. Simulating the quantum mechanical interactions between a drug molecule and a protein target is a problem of extraordinary complexity, one where classical supercomputers can only approximate, never exactly solve, at anything beyond very small molecule sizes. Quantum computers that can simulate these interactions accurately would allow pharmaceutical companies to design drugs computationally rather than spending billions on physical trial and error. The same principle applies to materials science. Designing new battery materials, superconductors, catalysts for carbon capture, and semiconductor materials all require understanding quantum mechanical properties that classical computers cannot model with sufficient precision. IBM and Riken's June 2025 demonstration that quantum classical hybrid systems are already beyond classical on certain molecular simulations is not an academic result. It is a signal that the pharmaceutical and materials industries need to start positioning themselves for a computing paradigm shift that is closer than they think. The cryptography implications are the other major consequence that deserves to be addressed directly and honestly. RSA encryption, the foundation of the secure internet, protecting everything from banking transactions to classified government communications to your WhatsApp messages. It relies on the difficulty of factoring very large numbers. Shor's algorithm, running on a sufficiently large and fault-tolerant quantum computer, would break RSA. A 2025 survey published in a major security journal found that experts estimate a 39% probability that quantum computers capable of breaking internet encryption could emerge within the next decade. That is not a certainty, but 39% is not a comfortable number when the stakes are global financial infrastructure and national security communications. Google's own spokesperson stated in late 2025 that they were still at least 10 years away from breaking RSA. But the trajectory of quantum hardware progress in 2025 alone, from Willow's error correction breakthrough to Google's verifiable quantum advantage, to Quantinuum's Helios achieving better than break-even error correction with a 2.1 physical to logical qubit ratio, was faster than nearly every prediction made 12 months earlier. And when experts are consistently underestimating the pace of progress, projections about 10-year timelines warrant healthy skepticism. So did this lab, or these labs, prove that quantum beats supercomputers permanently? The complete and honest answer is yes, on specific problem classes, with specific algorithms, in ways that can no longer be dismissed as artificial or unverifiable. And on the mathematical level, for problems like factoring and quantum simulation, the permanent advantage is built into the physics and the mathematics in a way that no amount of classical algorithm improvement can overcome. But does that mean all supercomputers are obsolete now? No, not even close. Classical supercomputers will remain essential for the vast majority of computational tasks for decades to come. Quantum computers are not replacing classical computation. They are extending it, adding a new layer of capability for a specific set of problems that are structurally intractable for classical machines. The word permanently is accurate on those specific problems, and it is premature as a general statement about all computation. The most important thing to understand is that the era where quantum advantage was purely theoretical is over. It ended in 2025. The labs have done the experiments. The papers are in Nature and in Science. The results are verifiable and reproducible. What comes next is the hard engineering work of scaling these systems to the point where the permanent mathematical advantages become practical industrial tools. And based on the pace of progress from 2024 to today, that transition is going to happen faster than anyone is comfortable predicting. Hit like and subscribe right now so you're tracking this story as it develops. Because the experiments that will define the next 5 years are being designed. In labs right now, the hardware roadmaps are accelerating faster than any analyst forecast. You will want to be watching closely when the next round of results comes in.